Great, I think we're live. Hello all, and welcome to the 2021 Careers in Quantum Tech event. My name is Alex Challens, and I'm the CEO of the Quantum Daily, the leading provider of news, information and data on the quantum technology market. We're delighted to have everyone here today and are looking forward for a very productive session for both employees and employers. It's interesting, the quantum technology market has seen profound changes over the last few years. We've seen significant increases in commercial interest. We've seen massive increases in government support, and much needed, and some absolutely astounding funding rounds in the capital markets. And throughout all of this, one thing has actually remained consistent. For all of the complexity of this underlying technology that we all know and love, all businesses are ultimately driven by talented people. And so today is about connecting these talented people with their future employers. And we've been really humbled by the support from our sponsors in making this happen. We encourage you all to check out their profiles and booths. These are the companies that are proactively driving forward with hiring. At the Quantum Daily, we're delighted to partner with Eureka. Araceli has been a pioneering figure in helping employees and employers with training, skills, and recruitment. And she has built up an outstanding reputation in the industry for building the quantum ecosystem globally. So look, thanks again everyone for joining, and I'll let her provide a deeper introduction to the day.
Thank you very much, Alex, and welcome everyone. I'm really excited to be here. As some of you might know, we had our first careers event last year where we focused in UK companies, and we wanted to do something bigger, something global. And well, it's really big because we are talking about 1,000 people registered to this event, which is amazing. So I'm really pleased to have worked with you in this collaboration, Alex. So first of all, I'm going to give you some logistics information about how the event will work. So let me share my screen. Okay, so this is the agenda, and I know that there's people from all over the world and the time zones are a little bit tricky. So I tried to put both time zones. I have the East time zone and the Central European time, so then you can work out what your time zone is. So we are now in the intro welcome section, and then we have the fantastic lead talk by Quantum Machines. Then we will have 2 keynote talks, and then 5 short talks. All these from our sponsors, from amazing quantum companies from all over the world. They will tell you all what you need to know about the companies, about the open positions, what they are looking for, and all advice to really boost your career in quantum technologies. After that, I will give you a little bit background on the quantum technology landscape in terms of skills. What do you need? Think about your CV, think about your career, think about your life. And during all this time, you can do a lot of different things in this virtual platform. You can network with other people one-to-one. I will explain how this works. You can visit the booth, and it's not you can visit, it's you must visit the booths, because it's the thing that you need to do here. It's the amazing opportunity that you can sit together for a talk with people from these amazing companies and discuss with them what they are looking for, whether your skills and your profile can fit in what they are looking for. It's just that opportunity that you don't have unless that you sit with them and just shoot your questions. That's really what we want. That's really the aim of these sessions. So the booth will be open from 1:15 East time, and throughout all that time you can visit the booth, or you can decide to stay in the talks, whatever you want. The event will end at 5 p.m. East time or 11 p.m. Central European time. Now, how does it work if you want to visit the booth? So you will see that in the event you have a reception, schedule, lounge, and booth. You go to booth, you will see all our company's booths, and then you decide which one you want to visit. Probably the best is that you visit all of them if you're interested. So you will choose one and you will enter. Here you have the example for Quantum Machines. So you will have information about the company. So you can have a look at either the links that they provide to some information or the videos. But here, what is important is that you should sit down with them and talk to them. To do that, you see there are different tables. So you request to join a table. You will see how many people are sitting on the table. It can be that the table is just 2 chairs, so only one person will be talking to you, or you can decide to join a table with more people. So somebody will let you in, and then you can decide whether you want to put just your audio and your video on. I will suggest that you put your audio and video, because this is really an informal chat, and you can ask anything you want, but this is really the chance to have that informal chat with these people from these amazing companies. So if you are unsure about how anything works or whatever, just write in the chat or in the notifications, in the feed, anything, and we will see it and we will answer you. You also see that you can see all the people connected, and you can find us and write us a private message, and we will try to figure out if you have any issue. And then the speed networking and lounge area. This is going to be available all the time during the event. In the lounge area, you also see the tables as the one in the booth, as I showed just before. You can decide to join a table there, where you can find people from companies or other attendees that are sitting in the table. It's really similar to, when in an actual event, you will go and have a coffee and sit with someone that you don't know. You can do that. You can also have this speed networking that you see here at the top. You will just click on Start Networking, and you will be paired for 10 minutes randomly with another person. Here, of course, the amount of people who are seeking for jobs is much, much larger than the amount of people from companies. So if you want to be paired with a company, you need to be patient. So the best is, if you want to talk to people from companies, go to the booths. If you want to randomly talk to people, just meet randomly people from all over the world who are also looking for jobs. I suggest that you network a little bit. I think it's an amazing experience, and we always have very good feedback. So that's all what I want to tell you. I hope that you enjoyed the event, and I think we are ready to start with the first talk. So, well, I think it's time. I invite Elisha Svetitsky from Quantum Machines. Quantum Machines is our lead sponsor. Elisha is a quantum control solutions engineer at Quantum Machines. Prior to joining Quantum Machines, Elisha did his PhD at the Hebrew University of Jerusalem under the supervision of Professor Nadav Katz, writing his thesis on dynamics of 4-level Josephson qubits. Elisha, welcome.
Thank you. I'm going to share my screen.
Perfect. Okay. Good luck.
There.
I disappear now.
Great. Thank you. So as you just heard, my name is Elisha Svetitsky. I'm a quantum control solutions engineer here at Quantum Machines. My background is in superconducting qubits before joining Quantum Machines. And this is really an exciting time to be a physicist. Traditionally, when a physicist transitioned from academia to industry, it involved saying goodbye to quantum mechanics and never seeing it again. But now you can actually take all the years you spent thinking about quantum mechanics and learning about quantum mechanics, and you can actually use that and leverage that in your next step. So this is really a great time to be alive. I'm going to be talking about Quantum Machines, my company, and I'm going to say from the outset that we have many, many open positions. So if this presentation resonates with you, I invite you to reach out and contact us. Okay, so who are we? We are quantum physicists and engineers on a mission to revolutionize quantum control and unlock a new era in quantum research. The company consists of about 50 people, including a group of experimental physicists with backgrounds in almost every major quantum platform. Besides physicists, of course, we have programmers, we have engineers, but we're all focused on quantum control. That's the only thing we do. We're not a test equipment company. We don't do generic electronics. We do only quantum control. That is the only motivation for what we do. So I'll motivate our main projects. If you have a quantum system, that's some coherent qubits, it's not really enough to do anything useful. You have to be able to interface with the system. You have to be able to send pulses and receive pulses. Now, we are not quantum beings, we are classical beings. So to interface with a quantum system, we need some kind of a classical system to be there for us. If you Google classical system, you find something like this, a classical orchestra. And this is actually pretty close to reality. In a real quantum lab, you typically find many different instruments. And these instruments are synchronized somehow, and there's some orchestration going on. And these guys are going to execute the experiment. Now, you can do a lot of really amazing things with these kinds of tools. All the past few decades of quantum experiments have been done with them. And they took us pretty far. But eventually, you're going to hit a wall, okay? Because quantum systems are so different that they really deserve their own kind of control system. If you try to force and repurpose generic electronics to quantum experiments, eventually you find that the synchronization between the different tools is insufficient, or the communication times, and it introduces too much latency. If you're trying to scale up and you have a huge pile of AWGs and digitizers and so on, it becomes unwieldy and impossible to debug. So what we need is a quantum control system that was designed for quantum from the ground up. So as we like to put it, these traditional instruments took us to the highest altitudes on Earth, but now we want to take off, and that is what we're here to do. So we need a new control paradigm, and this is the quantum orchestration platform. The quantum orchestration platform is about being able to run the most advanced quantum algorithms out of the box with no effort from a super intuitive programming language. Now, I'm going to break this down, but the philosophy of the company is to guarantee the quantum control side of quantum experiments. Quantum experiments involve many different aspects. You've got fabrication, you've got the cryo, you've got developing the protocols and the algorithms and so on. The control side is something that we want to guarantee. So the quantum orchestration platform consists first of dedicated hardware. Okay, this is not an AWG with makeup rebranded for quantum. This is something built from the ground up, which interfaces with the quantum system. The dedicated hardware consists of a pulse processor, an FPGA-based system with unmatched capabilities, which I'll get into in a moment, which is responsible for executing experiments on its own. It doesn't have to communicate with other devices. It doesn't have to constantly communicate with a PC via some software. So what do we want a pulse processor to be able to do in order to say that we have some universal quantum control system? First, it has to be able to generate waveforms parametrically. And parametrically, I mean if we define some kind of pulse, then it has to be able in real time, while the experiment is underway, it has to be able to stretch, say, the amplitude or the duration of the pulse. It has to be able to change the frequency or the phase. It has to be able to do all this without another waveform being explicitly uploaded. Another capability is, of course, waveform acquisition. We have to be able to measure the response of a quantum system. This involves the ADC, it involves integration, demodulation, etc. Another capability is real-time processing. You can take measurement data and process it and calculate arbitrary functions of that data. And finally, comprehensive control flow. If-else statements, while loops, switch cases, etc. Now, if we think of all these capabilities as spanning a space, this is the space where the most complex quantum experiments reside. What do I mean by this? Let's imagine the most generic quantum experiment that anyone can imagine. This would involve generating some pulse. Then we would like to measure the response of the quantum system. And then we need some real-time processing. We want to take the data that we just measured, not a Boolean qubit state, not 0 or 1. We just received some pulse from the system, so we have the amplitude or the phase. We want to take this analog quantity and run some arbitrary calculation on this quantity in real time on the FPGA. And then we want to take the result of that calculation and decide what the next step will be. For example, if the result of that calculation is greater than some threshold, play this pulse from that channel. If it's smaller than that threshold, play a different pulse from a different channel. Or we can also do something more complicated. For example, take the result of that calculation and use that to determine the amplitude or the frequency of the next pulse. So this is the most general kind of quantum control. And this is all enabled by the pulse processor. And it's definitely worth emphasizing that these capabilities are unmatched. They're unparalleled today in the world. No processor is this general and this capable. Now, it's not enough that we have these unmatched low-level capabilities. If I give you a blank FPGA and you're a brilliant programmer, then you can do amazing things with it. But these low-level capabilities are also very accessible, very, very easy to use. We have a programming language called Qua that we developed, which you'll see an example of later on. And the point is that this is a very easy language to learn, and you can utilize and exploit these capabilities very easily. Code that you write in Qua is then compiled via a proprietary compiler to the assembly language of the pulse processor. And that takes care, for example, of synchronization of different DACs and so on. So this is now an example of, this is some data that one of our customers took. This shows a Ramsey experiment. Now, a Ramsey experiment is not a revolutionary experiment. People have been doing experiments like this for a long time. But the pulse processor not only has these revolutionary new capabilities, when you use a pulse processor that was designed for quantum, even for traditional quantum experiments, you see a dramatic speed up. So what is a Ramsey measurement? This involves two pulses separated by some delay and followed by a measurement. So we have a pulse, delay, pulse, measurement. Now the x-axis sweeps the delay time. So in every point along the x-axis, we have a different delay between the pulses, and the vertical axis sweeps the frequency of the pulses. Now, this plot used to take them 15 hours to generate, and this is with a traditional lab setup. And most of the time, there was just wasted on communication between different devices. So the pulse processor brought that down to minutes. Now, how did it do this? Let's think how let's think how a traditional AWG would run this kind of experiment. Every point on this plot is essentially a different experiment. You have to define the waveform, typically sample by sample, upload that to the AWG, and then you run that 1,000 times for statistics. And then when you move to another point on the plot, it's an entirely new waveform. You have to upload it again to the AWG. And just that communication time is prohibitive. The pulse processor doesn't need to do that. It just follows instructions. You say, generate these pulses, sweep this frequency from here to there, sweep the delay from here to there, and within a couple minutes, it spits out this plot. Because it does the entire experiment itself, it doesn't have to keep communicating with a PC. So that's one aspect which speeds up results. Another aspect which speeds up results actually utilizes some unprecedented capabilities for active reset. Active qubit reset means, imagine you've just done one shot of the experiment. Your qubit is floating somewhere in its Hilbert space. You want to bring it down to 0 for the next iteration, for the next shot. So how do you get it down to 0? Traditionally, people would just wait, say, 10 times T1, and then the qubit thermalizes somewhere very close to the ground state, and then you do the experiment. Now, for long-lived qubits, 10 times T1 is a very long time. And also, the best you can ever get is thermalization. So that's something that is going to limit the fidelity of the initialization. An active reset, in contrast, involves measuring the qubit. If you measure a 0, then great, you've just collapsed it to the ground state, and it's initialized. If you've collapsed it to the excited state, then you quickly apply a pi pulse and bring it down to the ground state. So this is called an active reset, and a crucial element here is ultra-low latency. You can't let too much time pass between measurement and the pi pulse. Otherwise, the qubit has time to evolve, and the pi pulse won't do what you want it to do. So the pulse processor implements an active reset with a latency of 200 nanoseconds. This is the best latency in the world. Okay, no other system can do an active reset that fast. And so the active reset saves you a lot of time when you're initializing the system as well. Now, how does this actually work? What are we actually doing here? Let's break down the quantum stack. The lowest layer of the quantum stack is the quantum processor. These are the chips with all the qubits. The layer above the qubits, that's the hardware stack, that's where we come in. Those boxes are called the OPXs. The OPX is the main product of the company, and that includes the pulse processor and a microwave front end. And you can stack these on top of each other for larger processors, and they work together seamlessly. The next layer is a server. The server can manage different experiments. It has the compiler. It's responsible for job queues, etc. The next layer of the stack is the user, the client computers, people sitting in their offices or beyond the cloud. So that was a bottom-up view. If we take this top-down, we have the physicist writing some experimental protocol. It goes to the server. The server compiles it to the assembly language of the pulse processor on the OPX, and the OPX takes it from there, conducting the entire experiment. Now, from when the program is compiled to the OPX and we hit play, software no longer plays a role in the experiment. Everything happens between the quantum processor and the pulse processor. There's no more software involved, no other lab equipment involved. And this is what we define to be a quantum machine. A quantum processor and a pulse processor, each of them separately is not very useful. In order to do something useful, a useful quantum machine involves both a quantum processor and a pulse processor together. So this is not a coding boot camp, okay? So I'm not going to get into the programming language Qua, but it is important for me to impress upon you how easy it is to utilize these capabilities, how easy it is to exploit the full potential of the pulse processor. So we start out with some configuration. You have to define the configuration of your quantum machine. This basically says what kind of elements do I have, what qubits, what resonators, what flux lines, etc. And it defines what cables are going where, and also what kind of pulses I'm going to be playing. Once I've defined that, I can write a program. So this program involves a loop iterating over a variable A. And in each iteration of the loop, I'm playing a pulse to a qubit, qubit 1. And in every iteration, I'm multiplying the pulse amplitude by A. So this is something that's being generated parametrically in real time on the fly. These are not pulses which I uploaded in advance with different amplitudes, something that the pulse processor is doing in real time. After playing the pulse, I measure the qubit. I measure the qubit by applying a readout pulse. Then I listen at the ADC. I demodulate the data with some integration weights and save the result as a variable I. Now this variable I, it's an analog variable. It's the result of the demodulation. It lives on the pulse processor. It lives on the FPGA. This is now accessible for anything I might want to do with it. For example, I can do some of the real-time processing that I mentioned before, like say I squared times cosine of A, and I can evaluate this conditional. Is this quantity greater than 10? Okay, this isn't a useful quantity, but it's just for the illustration. So if this quantity is greater than 10, play some other pulse to some other qubit. I could just as easily take this quantity and say, and put this quantity into the amplitude of the next pulse, or into the frequency of the next pulse. So these are the feedback capabilities of the OPX. And this is how you get 200 nanosecond latency. You don't need to be a brilliant FPGA engineer to configure the system. You write 2 lines of code, and you have the active reset with 200 nanosecond latency. Now, the quantum orchestration platform is designed to be platform agnostic. Okay, people in our community typically have very strong opinions about which qubit realization is going to win the race and be part of the first quantum computer. But we are compatible with all of them. We are scale agnostic. Scale agnostic is not merely scalable. Scalable is a bit of an obnoxious term because it doesn't really mean anything. Almost everything is scalable in some sense of the word if you're willing to work hard enough. Scale agnostic means you can run 5 qubits just as easily as you can control 5,000 qubits. If 5 qubits need 1 OPX, 5,000 qubits need 1,000 OPXs. It takes a little longer to connect all the cables, but you write the code just as easily. You don't have to worry about synchronizing different DACs. The compiler does everything for you. This is scale agnostic. And finally, future agnostic. The low-level capabilities, the low-level architecture is extremely flexible. So if a couple years from now, people realize that in order to do an effective surface code, or in order to scale up cat qubits or whatever, we actually need some capability that no one has considered in the past, we're not going to start over from scratch. We are future agnostic in the sense that we are ready for anything that the future might throw our way. And of course, the ultimate goal of the community, of the industry, and of the company is a major quantum computer. So here we see a large-scale quantum processor along with a large-scale pulse processor. Okay. Now, Working with quantum machines, what we offer our customers, first of all, it's the time to results metric. Okay, when you get a pulse processor and an OPX, how long does it take you to actually utilize and exploit all of these capabilities? So the capabilities the OPX offers are unprecedented, they're unmatched, and it's also very easy to use. So if you have some idea for a quantum experiment and you're not able to do it with your present equipment, this has happened many times in the past, we deliver an OPX, and within as little as a week, the lab already has figures to put in the paper. The next thing is to substantially reduce run times. As I showed with the Ramsey measurement, that's something that used to take almost all day, and now it takes a few minutes. Now, this has a quantitative and qualitative effect on your research. If you have some calibration measurement that takes an hour to do versus a minute, then you're not going to do it as often, or it's going to be a bigger part, it's going to be a bigger headache and a bigger bottleneck. Qua, the extremely powerful and intuitive programming language, I think anyone who has spent time in a lab knows how important it is to be able to easily control your system, especially very complicated tools such as are used for quantum control. We have a GitHub. We have customers sharing code with each other. We also have our own team of physicists who implement various protocols and publish them on the GitHub, so people are always sharing resources. We have a deep understanding of your physics. Okay, now this is a major feature that we offer, because typically in a PhD, if you're seeing something funky and you want to talk to someone from the company that made the equipment to consult with one of their engineers, then the best case scenario is you get an engineer who understands his own equipment. He can tell you what it's doing. We are way beyond that. We understand not only what the pulse processor is doing, we understand what you're doing. We are physicists, many of us are PhD physicists. We have a deep understanding of the physics that our customers are doing, and we often collaborate with them. And finally, we have a simulator, which is also an extremely useful tool when you're programming some sequence or some experimental protocol. You want to make sure that the pulse processor is really doing what you think you want it to do. The simulator is a cycle-accurate simulator. It simulates all the pulses, simulates overflows and latencies and everything. So it's extremely useful for fast debugging. So I'm going to stop there. All teams are hiring. As I said at the outset, we have many open positions. We have positions that are customer-facing. We have positions that are product-facing. If any of this speaks to you, please don't hesitate to reach out. And you can find me in the booth later on, the Quantum Machines booth. So thank you.
Thank you very much, Elisha, for this talk. I didn't know so much about what you're doing. It's really, really exciting. I'm just checking if there are any questions. So please use the Q&A on your right-hand side if you have any questions for Elisha and our lead sponsor, Quantum Machines.
If people don't want to ask in this forum, I'll be available in the booth for more private conversations. Also, other people from the company as well.
Oh, I see a question from Clara Teofilo. She's asking, who are your main customers right now?
So the quantum industry right now, it consists of academic labs all over the world, okay, from all quantum platforms, and also startups and enterprises and flagships. We're working with everybody.
Great. So Sushan Prusti asked, do I need a PhD in physics?
No, you do not. You do not. We have all kinds of people, yes.
That's a very important message. Nasir is asking, Qua is open source?
Qua is not open source. This is something we've developed, and we are developing further versions, but it is not open source.
Stuart McLaughlin is asking, hello, do you have any advice for a computer science student looking to get into quantum computing?
That's an interesting question. I don't have a computer science background myself, so I can't really identify with the challenges involved. I would recommend just studying physics, like adding as much physics as you can. And including technical things, because in the end, this is quite a technical field, especially now that it's in its infancy. 50 years from now, it might be enough to have a pure computer science degree, but at the moment, you still need to know a lot of physics. But as I said, I'm not a computer scientist myself.
Devika is asking, a lot of questions are flying in right now. I lost. Do you only solve physics questions? Any other areas?
I'm sorry, I didn't catch that.
Do you only solve physics questions? Any other areas?
So we have, there's quite a lot that goes into this technology. We have electrical engineering, FPGA engineering, software engineering, as well as a lot of physics. So there's quite a lot that goes into the R&D.
Okay, I see a lot of questions. I don't think we have time to go through all of them, okay. But two basic questions, I think they are very important. One is, do you offer any kind of internship? And the other one is, do you have any remote positions?
So yes, we do hire interns, and we encourage you to apply. And do we have any remote positions? Then absolutely. Okay, so we have people all over the world. We are based in Tel Aviv, but we have people in Germany, in France, the US, Canada. Geography is emphatically not a limitation.
Amazing. Okay, I think we are going to close there. I'm going to send Elisha all your questions so he can answer you one by one. Thanks, Elisha, again. And yeah, visit the Quantum Machines booth. They are going to be there, so don't miss it. Okay.
Great. Thanks,
you. And see you soon in the other session. Bye.